So last time we started working on these differential equations, okay? So a differential equation just means we have an equation and there's a derivative already stated in the equation. And usually we're trying to solve that. It means we want to get a function of y in terms of x that solves that equation. So we got this from somewhere, right? And what we first did with these is make a slope field. So here's the slope field that we made for dy dx equals negative x over y. And what we knew from the slope field is that the solutions have to be circles. So I knew that I had something of the form x squared plus y squared equals r squared. And if I knew a particular solution, a particular point that it passes through, then I would know which of the infinitely many circles is the solution that goes with this differential equation and this particular condition. Sometimes called an initial condition, but I think that is a misnomer. So let's find an analytic way to do that, though. So the graph is nice, it's good to understand, but a lot of these you can do an analytical solution. So what we do is we do something called separation of variables. So this is separable describes the type of equation it is. This equation is separable because what we can do to it is separate the variables. Right, or we solve by separation of variables. All right, so what does that mean to separate the variables? It means to part the x's and the y's. Put the y's on one side, the x's on the other side. So typically we're going to put the y's on the left, although you don't have to. So you can see it's a simple algebraic rearrangement to say that this is the same as y dy equals negative x dx. So to move the dx over here is really not trivial, but it turns out to work. And then everything else is algebraic. So basically you're just doing like a cross multiplying here. All right, and then what you do is you're going to integrate on both sides. But you're integrating with respect to a different variable on each side. We're going to integrate this side with respect to y. We're going to integrate this side with respect to x, which we can do because this one's a dy, that one's a dx. All right, so what's the antiderivative of y? It's y squared over 2 plus c. What's the antiderivative of negative x? It's negative x squared over 2 plus c. Now we're going to really play fast and loose with this c. The c's we never said what they were. Maybe this one's 4 and this one's 5, whatever. We don't know. So we can just combine them into a single c, and we're just going to call it c. So basically these two c's, like we can combine them. We can do other things like, I don't like the 2's in the denominator, so I can multiply both sides by 2, right? But I'm not going to, oops, that's a negative. But I'm not going to say this is 2c. I'm just going to say it's c. It's a different c. This c, this c, this c, and this c are all different, okay? But it doesn't matter what they are, so we don't specify. And that's sort of how we work with the c. It's a little counterintuitive, but you know, if you want to be really careful, you go c1, c2, and this is c3, and this is c4, okay? They're all different c's, but it doesn't matter because we're not specifying what they were. We solve for them at the end if we need to. All right, and then I'm going to just put the x squared to the other side, so I have x squared plus y squared equals c. And then, look, that's what our general solution was. X squared plus y squared equals r squared. Now, we didn't know that the c, we don't know here that the c is the square of the radius, but it doesn't matter. That's just a redesignation of the variable. R is a constant, c is a constant. So now, what if we wanted to recover the particular equation that this came from? So let's say I knew that, right, this again specifies the infinitely many circles because I'm not saying what the c is. So I'm saying I have a circle centered at the radius, but I'm not saying, circle centered at the origin, but I'm not saying what the radius is. So it could be any of these infinitely many circles. So how do I specify that one of these circles is a particular solution that I want? Well, you would have to know one point on the graph. So let's say we have, so I'm going to call it a particular condition. And that particular condition is going to be the point 2, 0 is on the graph of the solution. All right, 2, 0. Or I could say 0, 2. I think I wanted to say 0, 2. It doesn't matter. All right, so some people call this an initial condition. I resist the phrase initial condition because initial condition is specifically time dependent and specifically refers to the time t equals 0, right? So that would always refer to t equals 0. But we don't necessarily have t equals 0. T is our independent variable. The independent variable doesn't even have to be time, right? I just have an x and a y. The x doesn't have to be time, and the x doesn't have to be 0. So that's why I don't like the phrase initial condition, because it implies that the x value is time and that it's 0, but it doesn't have to be. So I like to use particular condition. So all we need to know is one particular point on the graph, and that will distinguish my solution from all the other solutions. All right. So to use that particular condition, then I just take just like we did with accumulation. Wait, what problem was that? I guess it was when we did the advanced particle motion, right? If we know a particular time, then we're going to plug that in and basically solve for the c. So using that particular condition, I can say that 2 squared plus 0 squared equals c. So now I know that the c is 4. And so now I can put that back into my original equation and say my solution is x squared plus y squared equals 4. Now that x squared plus y squared equals 4, if we go all the way back to where we started with this, that is in fact the equation we started with. And so our initial question was, could you reverse this? Yes. You would need to supply information. So from the dy dx equals negative x over y, we now have a pretty simple analytic process by which we can get part of the solution. But then remember, we need to supply information. So as long as we supply the information in the form of a particular condition, sometimes called an initial condition, we can recover completely the original equation that this came from. And that's what we mean by solving a differential equation by separation of variables. Now, one last bit of vocabulary. If we don't have a value for the c, this is called a general solution to the differential equation. And once we do determine the c, then that's called a particular solution. So it's one out of the many solutions, right? So typically, if you don't have an initial condition, all you can get is a general solution. If you have a particular condition, then you get a general solution and a particular solution. So these are sort of similar to an indefinite integral and a definite integral, but not exactly. All right, so that's the process of separable differential equations. We'll look at some more examples of that next.